Hey everybody, it's me, Steve, and I'm not gonna lie here. This is gonna be a long one. I was gonna break it out into parts, but I just figured it was easier to put it into one video. That way, you're not losing anything. If you miss one, it's no big deal. You can always fast forward through it if you want. Most people, I'm sure, will, because how long I know this is gonna be. But anyway, what's the purpose of this video? Well, um, plate tectonics. Most people have heard of it, have studied it, or have heard of it in a science class in high school or taken Geology 101. And it's basically the process of how Earth loses its internal heat. But the plate tectonics of today has not always been. And these 5 questions here are what I'm attempting to answer in this video. Well, kind of I want to share with you the present understanding and where uh, the human understanding of plate tectonics extends back through the entire history of the Earth, not just since Pangea. Everyone knows of Pangea and all the continents split, and that's Paleozoic stuff. But that isn't always how it's been. Um, and so I've came up with these 5 questions in order to help you understand of what our present knowledge is and how I perceive things are. Because there's still a lot of unanswered questions. And there's more unanswered than answered. And I just want to share what I know about plate tectonics with you in the history as it stands so far. And as always in these, I will if I take something from a professional paper or a source, it will be included on the slide. But anyway, let's get started on this. Okay, first question: how does plate tectonics work? Um, First of all, I need to define some things here. Okay, I'm going to use these definitions because not everyone has the same definitions either. That's the problem when you're dealing with a theory that's well used and understood in present day, but as you go further into the past, it becomes muddier, so people put lines at different places and all this other stuff. But basically, here's the definitions that, because I'm going to mention these a lot, okay? Plate tectonics. It's the movement of the lithospheric plates over the underlying mantle and where the new and where. Wow. I'm sorry. Let's start over. And I wrote these. This is all right. Plate tectonics: movement of lithospheric plates over the underlying mantle, and where new lithosphere is created at spreading zones, and old lithosphere is returned to the mantle in subduction zones. It's a mechanism of heat loss through our planet. All right. Um, that's the simplest definition, and that's how I'm going to treat it. I'm not, and you'll see that other people have other definitions, but that's the one I'm going to use. It's the simplest, it's the most practical and usable. All right. Wilson cycle. A lot of people think the Wilson cycle is the same thing as a supercontinent cycle. It is not. The Wilson cycle is simply the opening of an ocean basin and its subsequent closure driven by plate tectonics. And we have a well established history of this going back into the Precambrian. All right. A supercontinent. All right. Now, this is going to get a little hairy because I'm going to define these in detail in a minute here. But basically, a supercontinent is a period in geologic time where the majority of continental landmass, but not necessarily all, has assembled together due to plate tectonics. I'm going to define this better. A lot of people think of supercontinent, they think of Pangea. Well, all the land masses are joined together. Well, even during Pangea, all the land masses weren't joined together. All right, that's a misconception, a common misconception. It's understandable, and you can have a supercontinent and not have a Pangea. All right. The supercontinent cycle. It's the quasi-periodic assembling and disassembling of supercontinents. And what do I mean by quasi-periodic? A lot of time we as human beings like things to be very repetitious and cyclical, and in a lot of science things are, if I am combining 2 chemicals together, I can predict how fast they are going to do that, and they're going to do that every time. And if I do it again and again, I'm going to get the same thing. All right. Physics same is a lot much of the same thing, but it's not that way with complex interacting systems. All right, because it's not that simple as a basic you know, oh yes, this leads to that, which happens and thus, and so forth. That's not how nature works. What I mean by quasi-periodic is there is some sort of periodicity to it, but it's not a definite predictable. And we run into this when we hear about the Yellowstone caldera a lot. People sit there and say, oh, yeah, it's overdue for an eruption. Every 600,000 years it's supposed to go. It's a cycle. No, it's not. That's not what a geologic cycle is. It's not that accurate. It's not that precise. Yellowstone isn't overdue for anything. All right? It will blow when it blows. When we say periodic in geology, we're talking about plus or minus a significant amount of time. And supercontinent cycles the same way. But I'm going to show you, I'll get into it in a little more detail here in a little bit. All right, so how does plate tectonics work? This is a cross section just through the earth, just a section of the earth cut away through the crust and mantle. I know it's just a simple cartoon, but I want to keep things simple for everybody, okay? What you see here, the gray is the oceanic crust, the light tan is the continental crust, the red is the mantle, and the darker red's the mantle, the lighter red is an actual magma mantle plume. All right. Remember, the mantle is a solid. It's a warm solid that behaves like silly putty, but it's still a solid. Okay. I left the oceans off here for simplicity purposes, but they are an intricate part of the tectonic cycle. All right. So what do you have here? This is I'm presenting you here our mechanism for plate tectonics. This is what we think is happening. Okay. Well, sorry, excuse me. You get the mantle being hotter at the core. The core is still cooling. It's still giving off heat. There's still radioactive decay generating heat, so this heats the under mantle. And just like boiling water in a pot, you'll get parts that rise, and as they cool, they fall. So the mantle convects, all right, and loses the heat through convection. Well, what does this do? Well, as this comes up, and some of the rock will melt because the melting temperature of rock is dependent on multiple things. It's not just temperature, it's also pressure. So as deep, well pressurized magma in the mantle comes up towards the crust, that release in pressure may be enough to just melt it. And so you get magma. See, and here it is showing you rising here. All right. Well, eventually something's got to give because this is just going to keep coming to the surface. So, as you can see here, the ocean crust has cracked. All right. Now, gravity does play a very important role in plate tectonics, but for this simplistic illustration purpose, I'm doing how with the rift. I'm showing you how the rifting drives plate tectonics, although cold subduction, just the gravity of an old ocean plate, will cause these cracks on its own as the ocean plate gets thicker and denser and wants to weigh down upon the mantle. You don't need a plume to start this, all right? It'll just start to happen, okay? Well, sorry, I keep coughing. Well, as this magma plume rises to the surface, as you can see by the yellow arrows here, something's got to move. So the continent starts to split apart and push laterally across the globe. This also helps exacerbate the subduction of the gray oceanic plates back into the mantle as the continent widens due to the mantle plume coming up to the surface. And the process continues. The ocean slabs keep going deeper, and as you can see here, eventually what might happen is you'll get magma created at the subduction areas where the oceanic plates are here, and you'll get new continental crust or coming up to the surface as that melting occurs from the mantle. All right, that's all I'm showing you there right on the subduction border. All right, now I'm going to show you a rift, a textbook rift. All right, these are the basic 6 types of rifts. There's different types of junctions here. This is essentially them. I am going to focus on the RRR triple junction. All right, because that's the most common, and it's also going to be addressed later in this video. So what happens is as this magma plume rises up through the mantle, the surface cracks, well, it's going to crack in a certain manner. It's going to form a three-point junction, or your RRR junction. All right. Now here, I'm going to show you how this works. Now here you're looking down at the side at just some random blob of a continent. It's not any continent in particular. It's just to illustrate this point. You're looking down at the globe, so you're looking at a continent from space. As you can see, I included the curve of the Earth there on one side just to let you know you're looking down at the planet and not a cross section. So here you have your little continental blob. He's sitting there all happy, right? Well, rifting starts to happen, and as you can see, the same thing. The gray is the ocean crust, the light tan is continental crust, the red is going to be where your magma is upwelling, and as you can see, you get your gray cracks in your oceanic crust as this plume rises. All right. So your triple junction starts to form, and as you can see here, it comes up. Now what's going to happen is as this triple junction forms, it's going to release more pressure from under the mantle, and other triple junctions are going to form and connect. So your rifting has begun, and you're creating new ocean crust in the continent. That's what this gray area is in the middle of the continent. The yellow arrows are showing you how the plates are starting to move as subduction happens and this mantle plume is coming up at the surface. All right, and you can see I did those weird looking arrows are showing you that the old oceanic crust is being subducted under other ocean crust. It's not, I just can't draw an arrow going directly down, so that's what that is, and that's what the hash marks are. That shows you that the oceanic plate surrounding the continent is subducting under the surrounding ocean plates. All right. And so your triple junctions continue. Now what's going to happen? Well, these three arms, one eventually dies. It just stops functioning. As you can see, your other rifts are still rifting. You're getting new ocean crust, and at this point, the ocean will move in onto the continent. You'll start to get seafloor spreading at this point. But that light, one of those red lines has become tan because it's died. And we see this pattern in the coastline of Africa, Europe, North America, and South America as Pangea broke up. Okay, and you may get magma, just like we had in the cross section before, along the ocean trench near your teeth marks. You may get magma upwelling there through the melting of the mantle as that oceanic plate subducts back into the mantle. And your process here continues. Now, the other extending arms have died, and you've got an established rift zone here, like the Mid-Atlantic Ridge. That's this long red jogging line in the middle, but your continent is still moving apart. And here you get, on the west side by the ocean arc, where the magma came up, you see that new crust is being formed due to subduction. So this is basically what happens as a continent splits apart and things start to move about the globe. All right. So now I'm going to talk about the Wilson cycle. I'll let you read this, all right? But this is I got this from online, the source is at the bottom. I got this, I thought it was a good pictorial demonstration of how a Wilson cycle works, okay? Now, the Wilson cycle isn't a supercontinent cycle, like I said before. It's simply the rifting and ultimate closing of an ocean basin. Some ocean basins don't close, all right? Some do, and we have examples of this going back into the geologic past. We have the opening of the Huronian margin, and then the closing of the Huronian margin during the Pinocean orogeny. About 500 million years later. It essentially followed a typical Wilson cycle. The Huronian margin is a rift along the superior continent where a successful rift occurred, and then a couple 100 million years later, that closed again as another continent from what we think of the south, which would be Wisconsin and Illinois. Well, not really Illinois, but Wisconsin and parts of Minnesota and lower Michigan crash into the Upper Peninsula and Ontario. So that's an example of a ocean cycle, and one during the Paleozoic, would be the closing of the Paleotheous Ocean, the Paleozoic, the Mesozoic, as the continental fragment Chimera moved north, opening the Taos Ocean during the Mesozoic to Cenozoic. Now, some people have sat there and said Crimea was a supercontinent, but it was not. It was a continental fragment. It would even, if you saw this thing on a globe, I mean, the Japanese islands are bigger than this thing was. It was no continent on anybody's scale. And that's where you get into the whole, well, what's a definition of something and why we need better definitions of these things. So here we go again. A continent. All right, this is how I define a continent. A continent is a landmass where greater than one half of that landmass consists of one or more cratons, and that has greater than 3/4 of its continental shelf surrounded by ocean basin. I think that's a good solid definition. All right, well, what's a craton? This is Wikipedia's definition, and I'll let you read it. You can pause it if you want. I'm not going to go through it in detail, but that is actually a really good definition of a craton. So using my definition of a continent, we actually have 7 continents. I didn't think about this until I made my definition and started looking, because I am actually fascinated with Greenland. I would love to study the Precambrian rocks there, but so today's continents would be, using this definition, North America, Greenland, South America, Australia, Africa, Eurasia, because Europe and Asia are physically connected. They're a single continent, and Antarctica. So I guess we have 7 using my definition. Some people obviously wouldn't include Greenland. They would include it with North America. But if you look at Greenland, you see that it's surrounded by greater than 3/4 of ocean basin. So it would technically count as a continent. Size doesn't matter in my definition that much. Actually, it doesn't matter at all. So if you were going to say, like I mentioned before, Crimea, that could be classified as a continent because it was a continental fragment, but it was in no way a supercontinent. Okay, so here's a better definition of a supercontinent. Okay, a supercontinent is a tectonic term. All right, it's where greater than 2/5 of the planet's continental land masses have merged together into one single large continent. This does not include all land masses. This is just a majority, a big chunk of land masses. All right. So a supercontinent does not have to be all continental land masses joined together. This actually has never happened, and I've already touched on that. So I'm not going to beat that horse. But even during the Permian, when Pangaea existed, North China, South China, Indonesia, Crimea were all separate small continents. They were never joined into that supercontinent of Pangaea. This actually excludes the modern continent of Eurasia, which consists of about 36% of the world's continental landmass. So we're close right now to that 40%, but we're not there. This is another thing. I looked this up after I came up with this definition, but it's not quite there. If current projections hold, Africa and Eurasia will collide in about 35 to 45 million years, and Earth will have its first supercontinent since Laurasia broke up about 56 million years ago. And the Paleomagnetism project, you guys should really Google that and look at it. Scorsese is really good at this. Is like paleocontinental geography is like his thing, and he's really good at it. All right. So here we are going to go to the supercontinent cycle. All right, and there's the definition I gave before, or actually that one's from Wikipedia. So throughout Earth's history, here's a list of supercontinents. This first one, Ur. I questioned this one, and I put a question mark by it, and I failed to put a slide in here. But if you look at this reconstruction of Ur, it's very similar. Ur was a very small continent, and it didn't include the Superior Craton, like Ontario and the Upper Peninsula, which existed at this time. It's not in there. So it's not, even if this thing existed, it wouldn't have necessarily been a supercontinent, but the continents are smaller then too. They've been growing with time. But that's a talk for a different time. All right. Or if you look at its reconstruction, it looks very similar to a very narrow band in the southern hemisphere when Pangea existed. That's really coincidental, and the Earth isn't that regular, and it's probably not a very accurate reconstruction of it. This continent is still a hypothesis, even though I think it was a paper came out maybe 15 years ago about it, but no one's ever really studied it, and I haven't really heard anybody mention it very much. It appears in Wikipedia for some reason, and Wikipedia has it's just a mess of what's a continent, what's a supercontinent, and all that. So these are the ones that I know and I am familiar with, and I believe this will be far more accurate than Wikipedia's. The next, the supercontinents are in red. Large continent, or actually, I shouldn't say that. What's in red would be when you have nearly all, supercontinents together in a Pangea type situation. The black ones are just supercontinents. All right. We know Superior was there 2.8 billion years ago. It GA means billions of years ago, just so you know. When it merged with the big supercontinent of Kennerland. All right, Kennerland persisted for a while and broke up, and that's how we get the Huronian supergroup and all that. Columbia was the next one, and we don't have very good up to this point. We don't have very good reconstructions. We have bits and pieces of the picture, but not the whole thing, because the further you go back in geologic past, the more complicated things become because there's less evidence of it. Then you get into Rodinia. Rodinia is not argued as being. It was a thing. It was a Pangea type situation, and we have gotten a lot better. Like we're pretty good now. I think about our reconstructions of Rodinia. Up until about maybe 5, 6 years ago, there were a lot of different reconstructions, but I think there's been a general consensus now because we've got a lot more good paleomagnetism data, and I'm going to get into that later. Then you have Panatonia, and then you get Gondwana, which merged with Pangea, and then we get the familiar Pangea. And then Pangea begins to. I made the wrong Pangea red. I meant to make the other one red, but it doesn't matter. Pangea was obviously at a point when almost all land masses were together, but not quite. And then it starts to break up about 170 million years ago. So we get Gondwana land, which was a supercontinent, and Laurasia, which was basically North America and Europe and Asia. So that's just my list. And if you look down here, this was taken from Tectonics and Crustal Evolution. It's an actual paper. And it shows how supercontinents form. And I added some things to it, like I put a question mark. You look down here, it doesn't really look like we have a lot of zircons from there. I mean, was it really a supercontinent? Whatever. But you notice the zircons cluster when we have a supercontinent situation. And as you can see, if you look at this, it looks like every 500 million years about we get a supercontinental cycle. But if you start zooming in and studying it a lot clearer, you realize we don't, because we should technically be in the. I mean, if it was exactly every 500 million years, we know Pangea was 300 million years ago. We'd have a supercontinent at 800 million years, and we don't. And then we'd have another one at 1.2 billion years, which we do. But then we'd have another one at 1.7 billion years, which we really don't. Kind of, sort of, not really. See how this is not cyclical. Not precisely cyclical, hence the quasi regular periods. All right. But here are two constructions of Columbia, which is also known as Nuna. A lot of these have double names. I don't know why. But that's what, if you see those slashes, that's what it means. It means there's two different names. Columbia / Nuna, same thing. Here is the continental arrangements, suspected continental arrangements during that time, and as I've said, this was like 1.6 billion years ago. So this is just one person's interpretation I think it's personally, I think it's a good one, but Paleomagnetism in the future may, something totally different. And here's Rodinia, and we're pretty sure that this is really close. But as you can see, even Rodinia, even though it was a Pangea type situation, we still have significant amounts of land masses not joined all the way together. Columbia, if you look at Columbia, it's modeled as being all joined together, but that's just because we don't know where these little islands are, and some of these may not even have been there. Their positions may have been different. It's a guesstimate. But Rodinia is a lot more solid. Okay, so here's our second question. We're only to the second one in that initial slide. Was plate tectonics different in the past? Yes and no. This is actually still contested. The only general consensus is that plate tectonics of today was not in operation at the beginning of the Earth at all. There was no plate tectonics. You'll find no one who contests that really. But the real question is, well, when did it begin? And how did it work? That is still actually very contested. The modern mechanism doesn't seem to extend back into the deep Precambrian like the Archean. Okay, so we actually have a good understanding of modern plate tectonics, which is often referred to as rigid lithospheric tectonics. There's my citation, involving what we call cold subduction. I'm going to show you a slide that demonstrates that. Extending back to about 1.2 billion years. Now, these are my divisions. The next slide I'm going to show you, the guy divides it into far more. I think it's too complicated. I don't think that's necessary. I think these are good enough divisions. Okay, from about 2.5 to 1.2 billion years ago, we must have had a form of plate tectonics in operation because we observe Wilson cycles preserved in the rocks, the Huronian group, Macat Range supergroup, and known supercontinents, Kennerland, Nuna, and Rodinia. So Wilson cycle indicates plate tectonics is working. It's happening. All right, you can't have a Wilson cycle without plate tectonics. So is it that cold rigid lithospheric tectonics? Probably not, but it's close to it. We would recognize it as plate tectonics, all right? 3.5 to 2.5 billion years ago seems to be an intermittent stage between plate tectonics and a pre-plate tectonic system. We may have had what's called a hot shallow subduction regime going. I'm going to get into a slide that shows you that here in a second, so I'm not going to go into that yet. All right. 4.5 to, since the formation of the Earth, 4.5 billion years ago to 3.2 billion years ago, we aren't sure. It's possible it was a mantle plume system similar to Venus or something we don't know. The thing for sure is we did not have a plate tectonic situation in operation. We know this from many lines of evidence, diamonds being one. I've done a geo-rant on that, and numerous other lines of evidence. The fact we don't see subduction and rifting cycles, although there have been a couple papers out there where people have tried to push it back that far, but it doesn't seem, it breaks down. And then once one of those papers comes out, several papers come out sitting there showing how that doesn't work. But the common thing in people's minds that just know what plate tectonics is, and even amongst most geologists who don't study or look at this type of thing, they think, oh yeah, plate tectonics, it's been going on since the beginning of the Earth. No, it has not. And I've even seen that in an actually really good documentary, that Making of North America documentary, a year or two ago. They they extend plate tectonics all the way back to the beginning of the Earth, and it was not a thing then. We don't know exactly what was going on then, but it was not plate tectonics. All right. As you can see again, this slide here, the Tectonics and Crustal Evolution paper comes up again, and these are regimes of how the authors of this paper pictured the Earth losing its internal heat, because it wasn't plate tectonics, during the Hadean, which would be the oldest part of the Earth from its formation to, off the top of my head, I want to say maybe 3.8 billion years ago, during the end of the heavy bombardment, I think. But I could be wrong. It could be set at 4. I forget. The Archean was right after that. And as you can see, you start to see it evolving into something different. TTGs, now this is interesting. These are tonalite. In a nutshell, TTGs are tonalites. Prior to the late Archean, 2.7 to 2.9 billion years ago, we don't have any granites. They're all tonalites. Tonalite is closely related to granite. It just has almost no alkali feldspar in it. And that is another key clue that plate tectonics really wasn't happening. Because we have granites all over the place today and throughout the Paleozoic and the Paleoproterozoic and the Mesoproterozoic and the Neoproterozoic. So that's a clue that something else was going on. And then we have modern continental crust here. The longer column here on the top and 3 right there that shows you how modern plumes are suspected to work. All right. Now you see this black line here dividing the left from the right, and on the right we have the Precambrian plate tectonics criteria and evidence. And here they show you normal subduction in the top one. That's what happens today. Subduction, how the Earth recycles its oceanic crust, is a key to understanding plate tectonics. The problem with it is no oceanic crust. I believe the oldest oceanic crust on the planet is 260 million years because it gets recycled as where the continents do not. So it's kind of hard to study these things, but we know what's going on today. We can observe it through seismology, through bouncing lasers off the moon, measuring spreading rates of plates. So we can figure it out today. So we have this normal subduction thing going. And I mentioned before shallow subduction. Well, that's what this middle one shows. But shallow subduction has happened in recent times. We're pretty sure that once the ancient Rockies were being raised, that was a form of shallow subduction that became normal subduction as it got older. So it still happens. It's just not dominant like it may have been in the past. So that's what that middle slide is showing you. And the bottom slide is showing you what's called plume tectonics or mantle plume tectonics or mantle plume spreading. Or if you that's basically we aren't. There was subduction didn't exist like it does now. Rifting didn't exist as it does now. This is a plume-driven tectonic regime, which may be happening on Venus to this day. But this is just pure. It's a proposed mechanism. It's our best guess. It's really we can't show this for sure with how our present understanding of plate tectonics and our present technology and where we have looked for things. But I mean, we may figure out this is true or not. But it's just a proposed mechanism for pre-plate tectonic Earth. All right, we're on question 3. Has plate tectonics started and stopped again? And in the past 15 years, this question has popped up. And the answer is possibly. It has been suggested that plate tectonics may be an intermittent process. It is possible during the supercontinental assemblage that subduction may cease for short periods of time before starting up again, and I mean short period by geologic standards. And there's the paper I cite. One such period may have been from 2.45 to 2.2 billion years ago. I am not sold on this one at all. All right, and the main reason being is we have passive margins out there. We have the Cabral province in South Africa. We have the Huronian supergroup. We have the Snowy Pass supergroup in Wyoming that show passive margin development like you would expect at the beginning of a Wilson cycle. The reason why this has come about is because these Wilson cycles seem to have stopped halfway, then magmatism seems to have occurred without a plate collision. That doesn't mean one didn't happen. It could have been an ocean crust, just old ocean crust breaking and getting subducted, not leading to anything, being that shallow slab tectonic regime. So then the ocean crust would be gone. But we do still have like a complete Wilson cycle within a Huronian. It just didn't happen at 2.2 billion years ago. It happened at 1.8-ish. All right. And there's a period in Earth's history that is often referred to as the boring billion or the barren billion. There's a whole bunch of different names for it. But from about 1.8 to zero point 0.8 billion years ago, when there appeared to be a long period of tectonic stability as the supercontinents Nuna and Rodinia existed. During this time, we have accretionary terrains such as the ones that formed during the Pinokian, Yavapal, Mesitals. I've always had problems saying those two, and the Grenville orogenies. An orogeny typically occurs as two or more continental crustal fragments merge and form mountain ranges. We had the term orogeny around long before we even knew what plate tectonics was. This doesn't mean there was no plate tectonics going on. It just means you had very long period of tectonic stability. And in a supercontinental situation where you have most of the land masses joined together, like a Pangea or a Rodinia and possibly Erland, you may get periods of time where plate tectonics just stops because everything's pretty much merged together. Subduction has ceased as these continents have come together. So until new pressure and new crust, as that continental crust starts to sag with age, just like oceanic crust does, until you can get new plumes generated, you'll get a cessation of plate tectonics for a period of time. But is it like 300 million years like suggested in the first paragraph here? No, it's probably on the order of 50 million years at the most. I mean, you probably still get things like volcanoes, and you still have some residual subduction. And like I said, not everything is ever joined together in one continental mass. So things are still moving about the globe, just not to the extent. So there's no true cessation of plate tectonics, but there may be these huge hiatuses associated with it. All right, now I'm going to talk about some of these orogenies. You had the Pinokian orogeny, 1.86 to about 1.73 billion years ago. You ask different people, they come up with different dates, but that's generally the time frame, so that's accepted. And what happened to the Pinokian orogeny, here you see on the left, I'm using Wisconsin, you see the purple areas where two continents collided. The one on the top would be the Superior Craton. It would be that Huronian supergroup type sediments of the passive margin, and another continent came from the south, from Wisconsin, and collided with that. And this green area in the middle is that they where, and I don't want to use that word because I don't define it anywhere, but when the two continents collide, the ocean crust sediments will push up, you'll get volcanism going, and although the ocean plate gets subducted as a whole, there's residual stuff that stays, and that's essentially what that green stuff is. And here you see the Superior Craton to the right. The Trans-Hudson orogeny is just on that diagram, but here you have the Pinokian in tan, the Superior in red, and the Wyoming Craton. The important thing about the Wyoming Craton is that it's very closely related to the southern part of the Superior Craton, and this is a situation where we have a geologic dilemma here, because the two are separated by the Trans-Hudson orogeny, although due to lithology and stratigraphy, they should be connected, but that's also a dilemma for another time. All right. So here is the Yapval and the Mazitzal orogenies. This is just a depiction of those, of how those occurred, where those deposits are at. So we had orogenies going on in the Paleoproterozoic quite a lot. So we know we had active subduction. Now here's the Grenville, and the Grenville is going to come into play later here. The Grenville orogeny is a complex orogeny. Basically, the Superior Craton, which at the time was essentially North America, and you had these continental fragments assembling from the south, like in Wisconsin, due to the Pinokian orogeny and the Yapavile and the M1. You had these things assembling into what would later become North America. At the time it was called Laurentia. But the Grenville has several pulses because it's several fragments. Very complex. Probably more a modern analog would be like the east end of Asia and the Japanese islands. Except the Japanese islands are not continental fragments. Most of these were continental fragments. accretionary terrains is what they're called. So here's the pulses. This was taken from the Canadian Journal of Earth Sciences. So as you can see, there's several pulses, there's several sub-orogenies, if you will, associated with the Grenville. But I mention this because, like I said, it's going to come into play again later. During the Barren Billion, there are three large igneous emplacement events in North America, and I'm mentioning these now. I've been mentioning orogenies, subduction zones, continents colliding, building mountain ranges, but at this time, something else was really happening. We had a lot of massive granitic intrusions just building up continents from underneath, and we still don't understand why these happened. They may have been parts of rifting zones, and just the remnants or something. But they're huge, huge events. I've mentioned the Baraboo interval before, so I'm not going to mention it here. I've talked about it extensively. We also had the Wolf River event, 1.53 to 1.47 billion years ago, and this one was huge. We had huge magmatic emplacements in central Wisconsin, all the way down through southern Illinois, into Minnesota, into at least Iowa. All right, so this event was huge. It caused massive hydrothermal activity, and the Francis Mountains in Missouri, our time analog is chronologically equivalent to the Wolf River, and this next one, the Granite Rhyolite provinces. It may have actually been a Yellowstone type situation, but that's a lecture for another time. But another big, huge magmatic intrusion would be the Granite Rhyolite province, 1.46 to 1.26 billion years ago, often split into southern and the eastern provinces. But that's just for talking. That's just for the practicality of talking about them physically. They aren't much different. And this is what formed most of Illinois, a good chunk of Indiana, the basement rocks of these states, Kentucky, Texas, Oklahoma. Those basement rocks were formed by this event. So this was also a huge, massive event, but it's almost not exposed anywhere. The Baraboo and Wolf River are exposed pretty decently, but these Granite Rhyolite province, most of what we know is from seismic data, and maybe 100 to 200 drill cores that managed to go that deep, spread throughout 5, 6, 7 states. All right, then we have this last one, and this one's I'm going to talk about in detail later, so I'm not going to get into it here. We had the Mid-Continental Rift, 1.2 to 1.06 billion years ago. Well, the active igneous stage, there's sediments associated with that. And the rift is actually older than that and ceased after that, but the actual volcanic activities in that time frame is within 1.28 to 0.9 billion years ago. So you could argue that the Mid-Continental Rift is basically 1.3 to 1.1 or to 1 billion years ago. So 1.3 to 1 billion years ago. And down there, I have a definition for you if you want to read it. Now we're going to talk about the Wolf River event. On the right here, this is from Wisconsin Field Trip Guidebook. But if you want to read this, you can. These are dates and abstract from actual paper. What I have, I'm not going to read the whole thing, but what's in red, the Wolf River batholith is similar in age to other granites in southeastern Missouri, the Francis Mountains, and southwestern United States, and apparently a representative of widespread igneous activity that existed through the southern part of North American continent 1.4 to 1.5 billion years ago. So I've already talked about that, so let's go to the next one. Okay, what you see here is putting those into perspective. The purple areas here would be those granite rhyolites I talked to you about. All right, that's a granite rhyolite province. They have the Pinocchian orogeny on here, is this white area, but I put a red circle in the middle of that because that's where the Wolf River event was centered at, but was more extensive than that. the dashed hashed gray lines are those other accretionary terrains, those other orogenies I told you about. The yellow is Grenville and probably the closely related Lanao province. The green circle is just where the Francis Mountains are. The green line running through the Great Lakes, the green, dark green line, that's the Mid-Continental Rift. All right, and there's my sources for this. So, okay, we are more than halfway through now. Woohoo! So this was another one of the main questions. What is the Mid-Continental Rift, MCR, which is how it's commonly abbreviated, and its place in tectonic history? The Mid-Continental Rift has also been referred to, but to a much lesser extent, as the Mid-Continental Rift System, or MRS. People who study the Mid-Continental Rift, no one says MRS. I mean, nobody who studies it in detail and has walked the ground, everyone calls it MCR. It's kind of like Upper Peninsula. All the people who live in the Upper Peninsula, the Yoopers, they call it the Upper Peninsula. Everyone who lives outside of it calls it Northern Michigan. So that's how you know they're not from there and don't hang out there. But anyway, the MCR is a Mesoproterozoic rift that failed. Now, as most rifts we're familiar with are successful, like the Mid-Atlantic Ridge was a successful continental rift. All right. The volcanic stage of the MCR was active from about I've already said this, with a couple death throes lasting to 1.06. It immediately became filled with sediments, and those sediments are known as the Oronto and Jacobsville groups, which I study in detail and have written papers about up into the Neoproterozoic. These sediments, the Jacobsville group especially, could have been deposited as late as 0.7 billion years ago. Okay, this failed rift may hold clues to the development and fate of the modern East African rift, because there's a lot of debate about, is the Mid-Continental Rift one of those textbook R junctions that I mentioned earlier, and we're starting to lean towards it is. It looks really complicated, but as rifts form, there's different stages. I've actually talked about this before. The East African rift would be analogous to a second stage of a continental rift. The first stage, the beginning of rifting, would be more of an analog, would be the Basin and Range province in North America. Third stage would be more equivalent to what you see separating Africa and the Arabian Peninsula. The fourth stage would be a full-blown, seafloor spreading like the Mid-Atlantic Rift. The MCR didn't make it. It kind of made it in between where the East African Rift is and where the rift is that's separating Saudi Arabia from Africa. The ocean didn't quite make it through to it, so it wasn't a fully developed rift. The MCR wasn't anyway. Will the African rift become one? Who knows? Although we know it failed in the Lake Superior region, it possibly could have been partially successful rift elsewhere. And that's come up in the past couple of years. But here's the Mid-Continental Rift, just showing you, putting it into perspective for you how big this thing is. And it's kind of ironic because the continent tried to split here 1.2 billion years ago and failed, but 2.5 billion years ago it did successfully rift here, and the Huronians produced the Huronian supergroup. But fortunately for us, the rift failed, and we still have North America attached to most of itself. And that successful rift over a billion years before may have been a weak zone where this rift tried to form where it did. But here on the left, you see the gray hatched areas, the Mid-Continental Rift. The darker linear parts are the volcanics. Wait, I got that backwards. The lighter gray is the volcanics. The darker gray would be this sediment fill. I believe that's how that works on this one. And around, I chose this because around it you have dates from other surrounding accretionary terrains as North America grew from a north to south direction. And what this red is this is my addition, because since this figure came out, we have discovered a piece of the Mid-Continental Rift buried under Ohio and Indiana down to Kentucky through seismic, and that's what the one on the right is showing you. And if you notice, it stops right up against the Grenville front. And I'm going to talk about that a little bit more, but that's not coincidence. And off to the right, the color one, like I said, is the seismic profiling. I believe it's seismic. No, it's gravity map. Sorry, it's a gravity map. And they've highlighted the Mid-Continental Rift and where the Grenville front is. And then on the right, what's B, you see a diagram, which I'm actually going to show you more detail later. But C, you can see it's kind of similar to what's going on in the East African Rift. And the East African Rift may or may not become a successful rift, but like I said, the Arabian Peninsula has already successfully split from Africa, and that kind of linear progression of a rift expanding may show that the Mid-Continental Rift, if it is an analog to East Africa, that it may actually have been partially successful. And here is a selected mafic dike swarms in India and North America. And this is a PhD dissertation by a friend of mine, and it's been 2 years, so I know I can use it. I'm taking figures from her dissertation, and she studied this in detail, and she came to the conclusion that the Mid-Continental Rift is a standard triple junction thing. And this was basic abstract and introduction. If you want to read it, go ahead. I'm not going to read this verbatim to you. Now, you see here, she did this through paleomagnetism, and paleomagnetism is awesome because if you can get undisturbed igneous rocks, you can follow the path of where the continent was positioned on Earth. And that's what this diagram on the left here is showing you, dates and positions within margins of error. And we know how to take polar reversals into account because they were happening back then too. And her main focus was the Mid-Continental Rift. And but she did do some work which added to our understanding of that really old one, Erland, that supercontinent Erland, which I'll come back to in a minute. But anyway, on the right here you have where she puts the star is where the center of the magmatism stuff coming up from there, where this plume may have been centered. All right, that's what's showing you on the right. And you get all these dike swarms. Dike swarms are associated with rifting because not only are you going to get a triple junction, but remember how I said those triple junctions propagate? I showed you in the very beginning of this video. Well, these dike swarms are the initial stages of that. You'll get dikes coming up first and before you actually get the continent trying to split apart. And that's what a lot of these dike swarms really were, is they were the continent trying to getting prepared to split in other places. And there's other dates there in different colors of different dike swarms, just for reference. You can read all that if you wish. And the conclusion of this, her dissertation was obviously multiple parts. This was chapter 2, and there's a conclusion at the bottom. All right, now we're going to get into how the Mid-Continental Rift may have been partially successful. If you look at it and you see how it's bent like that, it's kind of forming a large triple junction, but it was segmented. It wasn't one large triple junction. There are legs to this. And here in the past couple of years, people have started to think, well, maybe Grenville, because the traditional theory was either Grenville, the rift started to form on its own, and the Grenville province moved in, slapped against it, and shut it off. Or the rift formed as Grenville approached Laurentia, and since crustal thickening wasn't occurring there or was occurring elsewhere, you got magma, maybe through shallow subduction, coming up and starting to form that rift. Either way, it was doomed to fail. That has been the traditional look at it. But in the past couple years, it may be that at least part of it was successful, that the triple junction parts we see are not the whole picture. Amazonia is depicted here. If you look in the figure on the right, this is the one I said I was going to blow up for you later. And you see the Paleomag in the top one, but on the bottom you see Amazonia. Amazonia is basically Brazil. And it's a couple little other places in South America, but basically it's Brazil. And at one point that was joined to Laurentia, or North America. And what may have happened was Amazonia, as it approached Laurentia, and the Grenville province had already assembled with it, the rift began for whatever reason, and Amazonia became a successful part and was rifted away, and then further compression through the Grenville or other accretionary terrains may have been what shut that the rest of the mid-continental rift off. Or it could be pretty typical that most continental rifts actually do not propagate through the whole continent and are successful. I mean, we know they are today because of the Mid-Atlantic Ridge, but that may not always be the case. That may actually be the exception, not the rule. Like East Africa, it's partially successful when we have ocean basin forming, but that may stop as you go further south. This may be that type of situation. I do still have my problems with this. The main thing being is the timing of the assembly of Amazonia to Laurentia and its rifting coincides really closely with some of those Grenville suborogenies I showed you earlier. So it's kind of like, how do you have something assemble to a continent like Grenville, pieces of the Grenville orogeny, at the same time you're pushing something away? Or how do those assemble fast enough and then something move and then move away, which would be, in this case, would be Amazonia. But it does work out. There's not a lot of time to do something like this, but there is enough time. And we'll see if this hypothesis pans out. All right. Some other part, remember I've mentioned Kennerland several times, even though this does not have anything to do with the Mid-Continental Rift. I like my Paleoproterozoic metasediments, like the Huronian and stuff like that. Well, she did some investigating in India as well. And here you see the projection here, and she has a lot of dike names and colors. And basically, down here at the bottom, she tells you what each of the cratons are. But that doesn't help somebody who doesn't know what she's talking about. You can see the continental outlines here. You can see India at the very top, then Australia. And that blob there, that's Laurentia. And the other provinces, they don't really have familiar modern looks. So I put here on the right for you basically what the superior craton's made out of. The Dewar craton, the Yilgarn craton, and that weird Scandinavian one I can never pronounce. So it is also, fortunately, that shield is also known as the Baltic craton. Shield and craton, those terms are interchangeable. They mean essentially the same thing. But if you notice here, you can see India during the initial breakup of Kennerland was at the North Pole. So even Kennerland didn't have every single landmass lumped together. India was separate. And Australia, and so it seems that basically Yilgarn, the Superior Craton, and the Baltic Craton made up the majority of Kennerland before it started breaking up. So India was not a part of it, but as you can see here, most of Kennerland was around the equator, we think. There's still a lot of paleomagnetism, other than what she's done here, has not been done on this. So it may, Kennerland's exact position still is not known. It may have been closer to middle latitudes, either northern or southern hemispheres. We really don't know for sure until somebody starts studying those 2.2 billion year old dikes that intrude the Huronian, and all those other ones. We really won't know for sure. So Kennerland is still anyone's guess exact configuration. So we have traditionally it has been assumed that the MCR failed during the Grenville orogeny when the Grenville province collided with Laurentia, North America. It has been assumed that the MCR just shut off. And Cannon was the first one to come up with that. Some others had suggested it, but he is a good guy, and he has really studied Lake Superior region. He knows his stuff really good. He's probably studied it more than anyone I'm aware of that's still living. This likely is the case, at least partially, and I've already addressed that. In 2014, it was proposed that the continent of Amazonia may have rifted from Laurentia before the Grenville collision. Like I said, the timing's kind of close, but I guess it works, and Stein has done a lot on that, and there's the reference for that. And the physical history of the Earth is still being deciphered. Although we have a good understanding of the mechanisms that shape our planet's surface, we're still in the beginning of our journey. New ideas and hypotheses are still being presented, and the theory of plate tectonics is still changing to fit the new data. And if you get anything out of this long rant, I want you to understand that more than anything. This is still a very virgin field of study, the pre-Phanerozoic plate tectonics. It's Phanerozoic being basic from the Cambrian to today. So this great mystery still looms over our heads. So there is still a lot to figure out about the history of our planet and how it evolved since its formation. It's not we are very ignorant of that time, and I'm hoping that I live long enough, I'm in my early 40s now, I'm hoping I live long enough to see that day when there is finally consensus on how our planet's internal heat has been lost through time and has led to plate tectonics of today. But that is it, and I hope that you did get something out of that.